And today we're going to talk about techniques of integration, and in the last video I posted, there was a video on how to use integration by parts, and hopefully you looked at that video. And the gist of integration by parts, it's mainly used when you are taking finding the integral of a product, right? If you have something times something else, which is a product, you could use the integration by parts method. Okay, and there were two techniques. There is actually the integration by parts formula, and there was also something called the tabular method, which seems a little bit easy when you're integrating using the integration by parts. Today we're going to take a look at integrals that deal with trig functions, some trig integrals. So here are some of the documents that you're going to need for class today. And I'm going to go back to the desktop screen. All right, so in our course, in this formula sheet section, you're going to need the integration tables. You're going to need the trig derivative formula sheet. And today we're also going to use the trigonometry formula sheet. Okay. Now this sheet is actually from a trig course, and as you're going to see as we go through, yes, this is what we're using today. And you're going to see as we go through, where was I? Okay, you're going to see as we go through integration of our trig formulas, we will kind of rely a little bit heavily on this trig formula sheet because we'll be using some substitutions, and we'll be using some things that may not be so clear on the surface. So once again, the three documents you're going to need are the integration tables formula sheet, the trig derivative formula sheet, and also the trigonometry formula sheet. Okay, and if we take a look at the integration formula sheet, okay, I closed one document now. But if we take a look at the integration formula sheet, I'm sort of concentrating on these trig functions. Okay, notice that the sixth formula is for the integral of sine, right, which is negative cosine. The integral of cosine is sine. Notice that there is no integral for sine square or integral for cosine square. There's an integral for secant square. There's an integral for cosecant square. Right? There's an integral for secant u times tangent u. There's an integral for cosecant times cotangent u. There's an integral for tangent u and cotangent u. Okay, notice that there is not an integral for tangent square. Okay. All right, so notice we have the integration formulas as follows. Now, if I take a look at the 6 and 7 formula for the sine and cosine, these formulas are very specific in that in order to integrate, let's say, the sine, your power for sine would have to be the first power, right? So there is no formula for sine to the second, sine to the third. That's what we're going to sort of work out today. Also notice that the coefficient of your argument is an understood 1. So for example, if you were asked to, let's say, integrate the sine of 2x, right, you couldn't necessarily use this formula because the coefficient would have to be 1. All right, so before we actually take a look at the techniques of integration, All right, there's a formula for sine, right? And this is a fact. There's a formula for cosine. We're going to work out the formula for sine square. Okay, you can jot that somewhere in this formula sheet. We're going to write out the integral for cosine square. And we're also going to write out the integral for tangent square. All right. So the first thing we're going to do is we're going to integrate sine square x dx. And you'll notice that there is no formula for sine square x dx on our formula sheet. In order to integrate sine square, we must first make a substitution for sine square. So if you've been following along in the homework and kind of looking at the viewing examples, they'll kind of give you the correct way to rewrite this. Okay, but this is how you would actually find sine square x. This is actually what we're substituting for sine square x. If I go into the trig formula sheet, I'm going to go down to these double number identities, and I'm going to use this identity. And I'm actually going to jot that on a separate sheet of paper. And this is just the double number, the double angle of sine, okay, or at least one of the double angle for cosine formulas. Notice that there's three. I'm going to use this third formula. So I'm going to write this down as a cosine of 2x. So I'm just going to replace a with x. The cosine of 2x, that's equal to 1 minus 2 sine square x. All right, and I'm not actually broadcasting. All right, so here again, I am on the trig formula sheet, and I'm looking at my double number formulas. And in particular, I'm looking at this last formula for the double angle for cosine. And it's written out as cosine 2a equal to 1 minus 2 times sine square a. I'm simply substituting a for x. I'm actually going to take this double angle for cosine formula, and I'm actually going to solve it for sine square. Right, so the first thing I'm going to do is subtract 1 from both sides. I'm next going to divide both sides by -2. And I'm actually going to flip this around. I'll just put this extra step in. So sine square x is equal to, and I'm going to rewrite my denominator as a positive. So I'm actually going to rewrite this as 1/2 minus 1/2 cosine 2x. And this is how I'm going to substitute sine square x. All right, so notice I took the double angle for cosine. I solved it for sine square. and I'm going to substitute into this integral. So the first thing I'm going to do is substitute. So I'm going to rewrite sine squared x dx as the integral of 1/2 minus 1/2 cosine 2x dx. All right, so if you're looking in a viewing example, this is where this comes from. In the viewing example, they simply just go from this step to this step. Okay, but there's an intermediate step, which is that double angle for cosine has been solved for sine squared. All right, so now we'll integrate it. So I'm going to distribute my integral operator. So if I were to integrate 1/2, I have 1/2 x. I'm going to bring down my minus. I'm going to bring down 1/2, right? I'm going to just pull that 1/2 in front of my integral operator. And over here, I'm going to integrate cosine 2x. All right. So I've simply taken my negative 1/2 and I push that in front of the integral operator. And now I'm going to integrate cosine 2x. So I want to make a substitution, right? Because we don't have an formula to integrate the cosine of 2x. We only have a formula to integrate the cosine of x, or the cosine of u. So I'm going to substitute u for 2x. So I can rewrite this as the cosine of u, right? But in order to substitute out the dx, I'm going to take the derivative with respect to x from both sides of my substitution equation. All right, so sorry for pushing this on the side. So when I integrate the left-hand side, I have du dx. When I take the derivative with respect to x for 2x, I get 2. I'm going to multiply both sides by dx. And in order to solve for dx, I'm going to divide both sides by 2. So now I can rewrite everything in terms of u. I can rewrite 2x as u. So this is the cosine, the integral for the cosine of u. And I can substitute dx for 1/2 du. And now I can integrate. The integral for cosine u is sine u, so I have 1/2 times the sine of u. All right, and since I don't have any limits of integration, I must add the arbitrary constant c. And next I'm going to back substitute, right? U is 2x, so this is equal to 1/2 times the sine of 2x plus c. So the cosine of 2x, the integral for the cosine of 2x is 1/2 times the sine of 2x, right, plus my arbitrary constant. So I can simplify this as 1/2 x minus 1/4 times the sine of 2x plus the arbitrary constant. So now we've derived this once. So now we're going to use it as a fact. Right? So this stands as a fact. The integral, and you can actually write this on the formula sheet, the integral for sine squared x dx is equal to 1/2 x minus 1/4 times the sine of 2x plus c. All right, so we have a formula for sine. Well, we have an integration formula for sine x. We also have an integration formula for sine squared x dx. So if you're ever asked to integrate sine square, this is your integral. All right, so here we're just sort of establishing some facts. So how do you integrate cosine squared x dx? All right, so if you refer to your formula sheet, you'll notice that once again, there is no formula for cosine squared, right? There's only a formula for cosine. So we're going to revert back to the trig formula sheet. So I'm still looking at these double number identities, and I want to look at this double number identity for cosine, the second one. It says cosine of 2a, and I'm actually going to write this down. The cosine of 2a or 2x is equal to 2 cosine squared x minus 1. So we're going to take this formula, we're going to solve it for cosine square. All right, so we're going to pretty much do the same things we did in the last formula. I'm going to solve this or isolate for cosine square x. So the first thing I'm going to do is add 1 to both sides. Next, I'm going to divide both sides by 2. And I'm just going to flip it around. So cosine squared x is equal to 1/2 plus 1/2 cosine 2x. All right, so I'm just using the divide by a monomial rule from algebra. It says that if you have a monomial in the denominator serves as a denominator for every term in the numerator. So I can actually write this as 1/2, 1/2 plus, okay, keep in mind there's an understood 1 for cosine 2x. So I can write that as 1/2 cosine 2x. So we'll make this substitution in our integral. So I'm going to rewrite the cosine square x as 1/2 plus 1/2 cosine 2x dx. Right, so the only thing that's really different about this problem and the other problem is basically the sign. So when we integrate 1/2 plus 1/2 cosine 2x, we should get 1/2 x plus 1/4 times the sine of 2x plus c. So notice if I integrate 1/2, I get 1/2 x. Here again, I would pull 1/2 in front of the integral operator, right? We previously integrated cosine 2x, right? We previously integrated that as 1/2 2x plus c, right? So the only real change here is the sign. Right? So we can establish this as a fact. The integral for cosine squared x dx, that's equal to 1/2 x plus 1/4 times the sine of 2x plus c. All right, so you may want to write this on your integration formula sheet somewhere. All right, the next integral we'll take a look at tangent square x. And again, we're just going to establish a fact. So when you see these things again, you can kind of refer back to your formula sheet or to these notes, okay, on how these things are worked out. So notice that there is no integral for tangent x. All right, which means I'm going to make a substitution. Now here's the substitution I'm actually going to make. I'm going to make this substitution with the Pythagorean identity, right? The second Pythagorean identity says that tangent squared theta plus 1 is equal to secant squared theta. I can actually solve this for tangent square simply by subtracting 1 from both sides. There is a formula to integrate secant square, right? So I believe I would make this as my substitution. Okay, but I want you to see where this is coming from. So I'm going to rewrite tangent square as secant square x minus 1. So I use a substitution to rewrite this as secant square x minus 1, right? This came from the Pythagorean identity. There is a formula to integrate secant square. And if you look on that formula sheet, the integral for secant square is tangent x. And the integral for 1 in this case is x. Since I don't have any limits of integration, I'm going to attach my arbitrary constant. So we can establish this also as a fact. The integral for tangent square x dx is equal to tangent x minus x plus the arbitrary constant. All right, and I want to do one more. This is not necessarily a fact, but I want to show how you can use these things to integrate. All right, so those three you can actually put on your formula sheet as facts. All right, so how do we integrate cosine square 6x? All right, so we have a formula to integrate cosine square x, right? But notice this formula is really specific. The coefficient for my argument of cosine is 1, not a 6. So in this case, in a similar fashion, we used cosine square x, the double angle formula. I'm actually going to use it here. All right. So this is for my formula, cosine square x. I'm going to put this x in parentheses. That's equal to 1/2 plus 1/2 cosine 2x. Right. So again, that came from and I'm just going back through our notes here. That came from this. Right. We simply took the double number for cosine, right, and solved it for cosine square. So in order to substitute out, I'm going to use this same formula, except for wherever I see a x, I'm going to substitute it with 6x. All right, so this is how I'm using this formula to rewrite this integral. So wherever I see an x, I'm simply going to replace it with 6x. So I have 1/2 plus 1/2 times the cosine of 2 times x, but I'm going to replace x with 6x. So I can rewrite cosine square 6x as 1/2 plus 1/2 cosine 12x. So this allows me to rewrite this integral as 1/2 plus 1/2 times the cosine of 12x dx. All right, so I use the double angle for cosine to rewrite cosine square 6x as 1/2 plus 1/2 cosine 12x. And now we'll integrate. So I'm going to integrate 1/2. So we have 1/2 x. Here again, I'm going to pull the 1/2 in front of the integral operator. And off to the side, I'm going to integrate cosine 12x. So I'm going to make a substitution. U is equal to 12x. I'm going to take the derivative and solve this for dx. So I believe I would have 1/12 du is equal to dx. Right, so I'm skipping some steps here, right? I took the derivative with respect to x for both sides. I multiplied both sides by dx and divided by 12. Right? So I can rewrite the integral of cosine 12x dx as 1/12 times the integral of cosine u du. Right, so I substituted 12x with u. I substituted 1/12 du for dx. Right, so this is equal to 1/12. The integral for cosine u is sine u and I'll back substitute u for 12x. So when we integrate cosine 12x, we have 1/12 times the sine of 12x plus c. And once we simplify, we have 1/2 x plus 1/24 times the sine of 12x plus the arbitrary constant. All right. Okay, so we've taken a look at how to integrate sine square, kind of where that substitution come from, how to integrate cosine square, and then how to integrate cosine square 6x. All right. So if you were actually, let's say, integrate sine square 6x or sine square 3x, you would follow the same process. You would use a double number formulas to rewrite first, okay, and then you would integrate. All right, so as you can see from the onset, if you're dealing with the trig functions, you may or may not have to revert back to the trig formula sheet to make some substitutions. All right, so now we will take a look at just some problems in general. Okay, here we're asked to integrate sine to the 6th power x times cosine x dx. And this should be similar to your number 1. Okay, in the section 3.2. Now, in the last section, we talked about integration by parts, and integration by parts was in fact used to integrate a product, right? And here we do have a product. We have sine raised to the 6th power of x times cosine x, right? Which is a product. Whenever you are integrating, the first thing you should always try to do, your first strategy would be to substitute if possible. Okay, now even though this is a product, we don't always have to use the integration by parts. All right, here we're going to make a simple substitution. So whenever you're looking at a product of trig functions, okay, in this case we're looking at sine and cosine, we always want to look at either sine by itself or cosine by itself. And here's the reason why. I can actually make a substitution to rewrite all of this in the u variable. Okay. So I simply want to locate the term that I have by itself, well, to the 1st power. So here I see cosine x. I'm going to make a substitution. I'm going to make my substitution as u equal to the sine of x. Now, one of the reasons why I'm choosing to make u equal to the sine of x is because the derivative for cosine is sine, right? So just by knowing that, I should be able to take the derivative and substitute this out with a du. So with the u being equal to sine x, I could rewrite this as u to the 6th power, right? Because u is sine x and sine x is to the 6th power. In order to substitute out cosine x dx, I'm going to take the derivative of my substitution equation So I'm going to take the derivative with respect to x for both sides. Right, so this is where the integral and that derivative sheet come into play. So the derivative for sine is cosine. So we have du dx is equal to cosine x. I'm going to multiply both sides by dx. So du is equal to cosine x dx. So that's going to allow me to substitute cosine x dx for du. All right, so notice we did not have to use integration by parts because we can substitute. Okay, now if you can't substitute, then you should look at integration by parts or either some other methods that we're going to talk about. Okay, so now I can integrate it using the power rule. So I have the integral of u to the 6 du. So u to the 6 is u to the 7 over 7 plus c. I can back substitute u for sine x. So I can write this as 1/7 times the sine to the 7th power of x plus c. All right, so notice here I was able to make a substitution. In all of the problems in this section, you should be able to make a substitution. Okay, we'll take a look at this example. We're asked to integrate cosine to the 6th power 3x times the sine of 3x dx. All right, so here again I have a mix of a cosine and sine. I want to locate the trig function that is linear, or that's to the 1st power. So notice this cosine is to the 6th power. This sine is to the 1st power. So I'm going to make my substitution based on this sine 3x. Okay. So sort of what we did in the last problem, I'm going to substitute u for the cosine of 3x. Right, so with that being substituted, I could rewrite this first factor as u to the 6th power. In order to transform the sine of 3x dx into the u variable, I'm going to go back to my substitution equation and we're going to take the derivative. So I'm going to take the derivative with respect to x. So on my left-hand side, I have du dx. On my right-hand side, I must use the chain rule, the outside-inside derivative. So if I take the derivative for the inside, right, the derivative of 3x is just 3. And if I take the derivative for my outermost function, the derivative of cosine is negative sine. So I have negative 3 times the sine of 3x. I'm going to solve this for the sine of 3x. I'm going to multiply both sides by dx. Right, so du is equal to negative 3 sine 3x dx. I'm going to divide both sides by negative 3. So negative 1/3 du is equal to the sine of 3x dx. So this is going to allow me to substitute sine 3x dx for negative 1/3 du. So now if we integrate, right, I have my negative 1/3 outside of my integral. U to the 6th power is u to the 7th over 7. And since I don't have any limits of integration, I'm going to add my arbitrary constant. I'm going to simplify. So this is negative 1 over 21, u to the 7th plus c. I'm going to back substitute u for cosine 3x. So we have negative 1 over 21 times cosine to the 7th power 3x plus the arbitrary constant. All right, now we will take a look at this example. The integral for a tangent to the 6th power x secant to the 4th power x dx. Now notice that for this problem, we're dealing with tangents and secants, right? So just like with sine or cosine, we either want to look for a secant alone or a secant to the 1st power, which we don't have. We want to look for a tangent to the 1st power, which we don't have, or we want to look for a secant square, which we don't actually have. Okay. And the reason why we would look at a secant square is because we can actually integrate secant square. Okay. And we can also find the derivative, or we can actually integrate secant square. All right, so since I don't have a tangent or a secant to the 1st, I can rewrite this as some type of secant to the 2nd power. Okay. So I'm going to rewrite this as the integral for tangent to the 6th power x times secant square x times another secant square x dx. Now this is one of the reasons why you won't want to either look for a secant to the 1st, tangent to the 1st, or a secant to the 2nd. It's because there's a relationship between tangent and secant to the 2nd power. So if I look at my derivative trig formula sheet, I see that the derivative for tangent is secant square. So I can make a u substitution. I can actually substitute u for tangent x. And when I take the derivative for tangent, I get secant squared x. All right, so here I'm going to let u equal to tangent x So if I take the derivative with respect to x for both sides, I have du is equal to secant squared x dx, right? So that would basically take care of one of my secant squares, right? So notice I could rewrite tangent x as u. I can rewrite secant squared x dx as du. But I'm left with another secant squared x dx. Okay. All right, so here's what I'm going to do to my extra secant squared x dx. I'm going to rewrite it. Right, so I'm going to bring this down. This is tangent to the 6th power x. I'm going to rewrite this secant squared x as 1 plus tangent squared x. And I'll show you where this is coming from in a second. And I'm going to bring down secant squared x dx. Okay. Now, I'm going to go back to the desktop for just a second. And if we look at this Pythagorean identity, secant squared theta is equal to tangent squared theta plus 1, or 1 plus tangent squared theta. Right, so I've taken the secant square and I use a Pythagorean identity to write it as a tangent square plus 1. Okay, so this is where that 1 plus tangent squared x is coming in. So now I can write this in terms of u and du. So we've substituted tangent for u, so I can rewrite this first factor as u to the 6th power. I can rewrite this second factor as 1 plus u squared, right, because we're substituting u for tangent, so tangent squared is u squared. We can substitute secant squared x dx for du. Right, so we have everything written in terms of u and du. So now I'm going to simplify. I'm going to remove the parentheses. I'm going to distribute. So this is u to the 6th power plus u to the 8th. If I integrate u to the 6th power, we have u to the 7 over 7. If I integrate u to the 8th power, we have u to the 9th over 9. Right, and then if we back substitute u for tangent, we have 1/7 tangent to the 7th power x plus 1/9 tangent to the 9th power x plus c. All right. Okay, so we've taken a look at a couple of examples that deal with products where we did not have to use the integration by parts method. We can simply substitute. All right, so here is the last example for today. I know this may be a lot to go through in one day. Okay, but there's some problems where in the homework, and if you're looking at their viewing example, they just kind of go from one step to the other without any clear explanations on things. So I want to look at this last problem, this last integral problem. Here we're asked to integrate sine 4x cosine x dx. Okay. And this is, I guess, is a special kind of problem because we can't use integration by parts, right? Because in integration by parts, you would treat one factor, you would integrate it, you would treat another factor, you would differentiate it. The factor that you choose to differentiate, you want to make sure that it differentiates down to 0, and neither of these is the case. So I can't use integration by parts. I can't use substitution, because if I were to substitute u for cosine x, it would be impossible for me to get this argument 4x. And then if I were to make u as my substitution, I'm still left with a 4x some kind of way. So it's impossible to use substitution, right? So where do we go from this point? Here again, this is where we have to result back to the trig formula sheet. Okay, so I want to switch back to the desktop screen for a second. And here were some formulas in the trig class. It probably didn't make a whole lot of sense to you. They were the product, the sum, and the sum, the product. And in particularly, we can take a product and we can re-express it as a sum. So remember that our integral was a sine times a cosine. So I'm going to use this third product of sum formula to rewrite our integral. So I'm going to just rewrite the formula first of all. So this is the sine of A times the cosine of B. That's equal to 1/2 times the sine of A plus B plus the sine of A minus B. All right, so here was the formula. And underneath the formula, I'm simply going to write my question. I have the sine of 4x times the cosine of x. And in this formula, I'm simply going to substitute A for 4x and B for x. So this becomes 1/2 times the sine of 4x plus x plus the sine of 4x minus x. So this becomes 1/2 times the sine of 5x plus the sine of 3x. All right, so this is what we're going to substitute in our integral. So this now becomes the 1/2 times the integral of sine of 5x plus the sine of 3x dx. So now I'll integrate the sine of 5x. Okay, I'll do that over here. So the integral for the sine of 5x, I'm going to make a substitution. U is equal to 5x. So 1/5 du is equal to dx. So I can write this as 1/5 times the integral of the sine of u du, and the integral for sine is negative cosine, so we have negative 1/5 cosine u plus c. I'm going to back substitute u for 5x, so that's negative 1/5 cosine 5x plus c. So when we integrate the sine of 5x, we have negative 1/5 times the cosine of 5x I'm going to integrate the sine of 3x. So I'll kind of do that here. The sine of 3x dx. So here again, we'll let u equal to 3x. So 1/3 du is equal to dx. So this is equal to 1/3 times the integral for the sine of u du. The integral for sine is negative cosine. So we have negative 1/3 cosine 3x plus c. So I'm going to write that in as negative 1/3 cosine of 3x plus my arbitrary constant. I'm going to distribute my 1/2, so I have negative 1/10 cosine 5x minus 1/6 cosine 3x plus the arbitrary constant. All right, so there's the trig integrals are kind of involved. Okay, as far as what you have to do, notice that I relied heavily on that trig formula sheet to make some substitutions. So hopefully this will help with this section. When we meet again on Thursday, we'll talk about how to make some more substitution, trig substitution, and we'll work with more trig integrals. All right, so at this time, I'm going to stop the recording.